Hello, welcome back, Calculus 2. We're in Chapter 10, and I'm moving into Section 10.2. This is a parametric equations. What I have is what we call a set of parametric equations. Sometimes I might just call it parametric equations, but they come together as a set. X is a function of t, and y is a function of t. And t is called the parameter. And sometimes I wrote this, a parameter is called a dummy variable. It's kind of a dummy variable. It doesn't seem too nice, but anyway. So immediately students might think, oh wow, we just jumped into a third variable, we're into a three variable situation. No, we're not, I'm sorry. This is the X, we'll do that in Cal 3. This is still the X and the Y axis, and X is still related to Y is still related to X, but they're related through this parameter T. So let's plot some points. If T is a -1, I can plug that in and I get -1 and I get -1 squared. So I get this ordered pair when I let T take on certain values. X was a -1, Y was a 1. If I let T be 0, I get the ordered pair 0, 0. If I let T be 1, I get the ordered pair 1, 1. If I let T be 2, I get the ordered pair 2, 4. That's probably enough. And maybe you've already got a little idea. Maybe you already got a little idea. If I plot these points, 0, 0, -1, 1, 1, 1, and 2, 4. I could plot more points. -2 is -2, 4. That might help. It's this parabola. It's this good old parabola. Maybe you already sort of saw that coming. But there's a little added feature here now. So again, I'm plotting the locations, X and Y, and there is no T doesn't show up anywhere on here unless you make these little notes, and you don't have to do this, but if you make these little notes that when you were here, T was -1. When I was here, that was T equals -2. This was when T was 0. I mean, I could jot down this little notes on the side here that tells me where I'm at certain T values. By the way, this is just a generic parameter T. It can mean anything. But it is convenient, it is helpful to think of it as time and to think of this as a particle is moving on this path. And so that's a cool way to think. I've just drawn the path as a particle moves on this path, and the particle is at these locations at these various times. And so one thing we like to do when we sketch a graph is we show orientation. We show orientation. And what that means is we show the direction of increasing T. The direction of increasing T. So T was -2, T was -1, T was 0. So as T increases, we are moving this way, left to right. So we put little arrows on here that indicate we're moving. That's the motion. That's showing orientation, is putting those little arrows on the path. So that's pretty cool. Maybe you knew a long time ago that this was going to be parabolic shape. Another little technique for analyzing parametric equations is we do something called eliminate the parameter. Eliminate the parameter. And when we eliminate the parameter, we're left with, this is a common technique, then we're left with the relationship between X and Y, which is what we call the good old rectangular equation. By the way, when we're working with X's and Y's, those were always rectangular coordinates. And so we start learning some new coordinates. We start learning some new language here in Chapter 10. So when you eliminate the parameter from the parametric equation, you find the rectangular equation, which is the relationship between X and Y. And it's easy. It's like a substitution game. Of course, you saw this one. If X is T, you can plug it in there for T, and you get the relationship Y equals X squared. So by substituting T equals X substituting that x in there, I eliminated the parameter. Sometimes it's more complicated than that. But we eliminate the parameter and we see what's called the rectangular equation. And that helps. But, you know, I want to say something. You know, this rectangular equation is cool. It gives me the path. It sort of gives me the path that I'm traveling on. But if I just draw a rectangular, you know, if I just draw this parabola, you know, we've always just drawn arrows on both ends because that indicates the parabola keeps going up, you know, in both. But now we've got this new thing to show orientation, direction of increasing t. We don't want to draw this. We want to draw our little arrows heading this way on this particular problem. Okay, that's a lot. That's a lot of cool ideas. The parameter t, the set of parametric equations, showing orientation, eliminating the parameter, plotting some points. You do have a graphing calculator that has parametric mode. You don't need it for this one, but it's fun for some problems. And it's fun to play and experiment. You can learn using that graphing calculator. Here's a question for you. What if I wanted this to go the other way? What if I wanted this to go the other way? I want it, as t increases, I want it to travel this way. And you could think for a while. You could come up with some different ideas. Maybe you already have. One common way to do that, there's maybe a couple ways to do that, but one common way to do that is to negate the value of t. So now I have a negative t, which means that also, I think now that means I have a negative t squared. Oh, but, right, because now if x is a negative t and I replace that with an x, I still have the y equals x squared, the rectangular equation, which I'm calling the path. I'm calling that the path that we're traveling on. But the way we travel on that path is a little different now, I guess. Now I'm going the other way. I think. Let me try something. If you plug in a -1 for t, oh, now you're at x is +1. And when you square it, it's going to be a +1. Right, now I'm over here. When t is -1, I'm here. When t is -2, I'm there. When t is 0, I'm still at the same place. So when t is a 1, I'm at -1, 1. Yeah, you're right. When t is a +1, when t is a +2. So that worked. Yeah, negating the t. Not negating both of them. I mean, just negated the t, which was the x, which made the x go backwards. And then the relationship between x and y dictated that it still traveled on this parabola. If I substitute this x in here and square it, I still have this relationship. Yeah, that's cool. Listen, these things get really cool. I love this parametric equations. Watch this one. X equals cosine t and y equals cosine squared t. That's a set of parametric equations. And let's analyze it. Let's talk about it. You might have already thought, you know what, if you eliminate the parameter by solving for t and substituting, actually, I'd rather not solve for t. I don't really have to get the cosine inverse and solve for t. I don't need to go that far. If x is cos t, can't I replace that x here, and don't I have y equals x squared? Right? X is cos t. That's an x squared. Yeah, so when I eliminate the parameter, I have the same rectangular equation. I'm traveling on this same path. So I'm still traveling on this parabola. But hold on, I want to show the orientation. I want to talk about this. But how am I traveling on this parabola? Let's see here. Let's see. I could plot points, that helps. Make a little chart and plot points, that sort of helps. I mean, that's a good way to do it. When t is 0, where am I? When t is 0, I'm at, cosine of 0 is 1, cosine, I'm at 1, 1. I'm at the point 1, 1. Kind of blew this up for you. So there I am when t is 0. When t is pi, or pi over 2, let's try pi over 2. When t is pi over 2, the cosine of pi over 2 is a 0, 0. Yeah, that's 0, 0. So here I am at pi over 2. What about when t is pi? When t is a pi, the cosine of pi is -1. When you take -1 and square it, it's +1. That's -1, 1. That's -1, 1. There you go. When t is pi. What about 3 pi over 2? Oh, I start heading back that way. So I just traveled this way. And so, you know, if I was looking to show orientation, I'm traveling this way. And I went from 0 to pi, and my arrows say there's the direction of increasing t. But I think as soon as I get here, I just turned around and started heading back. And guess what? I'm probably back to where I started when t is 2 pi. Let's talk about it like this. You know, what is the domain? What can you plug in for t as the domain? That's usually, you know, it can be restricted. It can have domain issues, but usually, like on this, you can plug in anything you want for t. What's more interesting is the range. What is it going to spit out? And not the range for y, but the range for almost each variable independently. So if you plug in any t you want, you know, the cosine of t only spits out answers between -1 and 1. So my x is restricted to living between -1 and 1. Right? You can plug in all kinds of angles for t. The cosine of an angle is something between -1 and 1. X is restricted between -1 and 1. When we drew this parabola, I could have thought about that way early, and I could have erased this big chunk of the parabola. It is traveling on this parabolic path, but it's only traveling on this part of the path. And how is it traveling? It is oscillating back and forth forever. I like to use that word. It is oscillating. Why is it oscillating? Because we've got this cosine parameter, cosine of t acting like my parameter. By the way, I just analyzed what x does. The y follows what x does. You know, the cosine squared is between 0 and 1. But I don't really have to analyze it. Once I've analyzed x and figured out what x is doing, this relationship dictates what y is doing. So that's cool, huh? All right, there's a lot of more coming here. Parametric equations. I want to talk about circular motion, elliptical motion. So stay tuned. Do some homework.